So picture a simple pile of sand sitting on a sidewalk, or maybe a stack of cardboard boxes in a warehouse.
Right, just something totally ordinary.
Exactly, just everyday clutter. But what if I told you that the shape you are looking at is, well, it's essentially a complete biological lie?
A lie. I like that.
Yeah, like the outline your eyes actually register is hiding this entirely invisible skeleton,
Yeah.
complete with, buried fault lines and structural tensions that are just waiting to collapse.
It sounds super dramatic, but I mean, it is physically accurate. We are so conditioned by our own biology to j- to to trust the silhouette, right?
Right.
We see a cone of sand and we immediately think, okay, that is a cone. But the source we are digging into today argues that the silhouette is almost totally irrelevant to what that object actually is.
Which is wild. So, welcome to our deep dive. The source we're looking at today is a fascinating paper titled A Gibsonian Theory of Accumulation Objects.
Quite a mouthful.
It is, yeah.
Yeah.
But our mission for this deep dive is to completely dismantle how you, the listener, view the messy, everyday objects around you.
Yeah, we're talking about piles, traffic jams, bridges.
Even the clutter on your desk. We are going to reconstruct all of it using this revolutionary concept called Gibsonian token dynamics.
Which I know that sounds like incredibly dense jargon right out of a sci-fi novel,
It really does.
but it's actually a deeply practical, really rigorous way of mapping physical reality. The core problem the paper points out is that our ordinary, everyday language for describing things that pile up is just, well, visually crude.
Okay, let's unpack this. Visually crude.
Yeah.
What exactly is wrong with looking at a pile of dirt and just, calling it a pile of dirt? Why do we even need a new language for this?
Because the way we have traditionally tried to measure and understand that pile of dirt using classical physics, I mean, it actually fragments the object.
Fragments it how?
Well, if you use standard continuum mechanics to study a pile of sand, you are essentially treating it like a weird liquid.
Wait, a liquid?
Yeah, mathematically speaking, you use geometry to talk about its shape, and then mechanics to talk about the pressure, and then statistics to guess how it might flow.
So you're just sort of chopping the object up into all these different mathematical vocabularies.
Precisely. Classical physics tries to smooth things out. It pretends that a pile of, like, millions of distinct individual sand grains is just a continuous, smooth material.
Which it obviously isn't.
Right. But the author argues for a completely different road here, the Gibsonian W-field calculus.
Okay.
In this framework, the discreteness is fundamental. You don't pretend the grains are a smooth fluid. You treat the pile as a network of distinct tokens.
Okay, so by tokens you mean the individual pieces, like the literal grains of sand or the boxes in the stack.
Every single piece.
Oh,
Because when you do that, you get exact bookkeeping.
right.
If a single grain of sand shifts under pressure, this specific math records exactly where it came from and exactly where it went.
Wow.
The author points out that under classical physics, all those little details just get lost to continuum approximation dust.
Continuum approximation dust. I love that phrase so much.
It's brilliant, right?
That's
Think of it like a rounding error in a massive banking spreadsheet.
Oh, yeah. A fraction of a cent here, a fraction there.
Exactly. In a bank, that rounding error might cost you a few dollars. But in structural physics, that approximation dust might be the exact microscopic instability that causes a retaining wall to completely collapse.
Oh, wow. Okay, so the Gibsonian calculus doesn't round anything off,
Nothing.
which means we have to stop looking at the outer skin of the pile. Like if a pile isn't just a scalar heap, meaning, just a shape taking up space, what is actually underneath?
Well, to understand the pile, we have to completely redefine what a single point or a site inside that pile actually is.
Okay.
It's not just a physical coordinate holding a piece of material. Every single site inside one of these objects carries a multi-channel discrete accumulation state.
Multi-channel, like a television.
Similar concept, actually. Instead of broadcasting one signal, every single point in the object is simultaneously carrying 6 distinct channels of information.
Okay, wait. 6 channels.
Yes.
If I'm zooming in on one single grain of sand sitting in a pile, what else is there besides, sand is here?
Well, sand is here is the first channel. That one is called occupancy.
Okay.
It's the physical amount of material, and it's literally the only channel our human eyes can actually see.
Gotcha.
But right beneath that, you have the second channel, which is packing density.
Which I assume means, like, how tightly squeezed together that specific spot is compared to the spot right next to it.
That's the one. And then the third channel is the lock state.
Lock state.
Yeah. Think of this as the effective support architecture. Like, how well is this specific grain propped up by its neighbors?
Oh, I see.
Is it resting securely like a keystone in an arch, or is it just balancing on a razor's edge?
Got it. Okay, so occupancy, packing density, lock state. What's the fourth one?
The fourth channel is shear debt.
Sheer debt. That sounds like a terrible anxiety condition.
Honestly, it is essentially structural anxiety.
Really?
Yeah, shear debt is the stored tendency for failure. It's tension that is just waiting to snap.
Okay, let me make sure I'm visualizing this correctly. Imagine two grains of sand rubbing together.
Okay.
There is friction holding them in place, but gravity is constantly pulling them downward.
Right.
So they haven't moved yet, but they really want to. That microscopic tension right before they slip, is that the shear debt?
You've nailed the mechanics perfectly.
Yes.
It is the physical debt of stress that the object owes to gravity.
Right.
And eventually, I mean, that debt has to be paid.
That makes total sense. Okay, what's next?
Now, the fifth channel is anisotropy.
Anisotropy. Okay, you're going to have to translate that one for me.
In the paper, it's referred to as the deposition fabric.
Yeah.
But to put it simply, it's the directional bias of the object based entirely on how it was built.
How it was built.
Yeah, imagine you're building a brick wall. If you lay the bricks perfectly flat, interlocking them carefully, they have an incredibly strong horizontal structure.
Right, a solid wall.
But if you just dump a wheelbarrow of bricks onto the ground, they're pointing in 1,000 random directions.
So the structure behaves totally differently depending on the actual direction the pieces fell?
Yes, exactly. The directional memory is the anisotropy channel.
Okay.
And finally, the sixth channel is cohesion, which is simply the natural tendency of the particles to stick together, like damp sand versus dry sand.
Okay, I have to play the skeptic here for a second, though.
Go for it.
If I am just, like, a construction manager or a warehouse worker, why do I need this hyper-specific six-channel discrete calculus?
Okay.
Isn't classical math already good enough at measuring a slope to tell us if a pile of dirt is going to fall over? This feels a bit like, I don't know, like judging a city's health strictly by looking at its skyline.
Oh, go on. How do you mean?
Well, you can look at a city's skyline, right? And the skyscrapers might look really tall and shiny. The geometry looks great.
Right.
But if you ignore the traffic flow and the local economy and the underground plumbing, you don't actually understand how the city works at all.
Exactly.
You wouldn't know if the city is thriving or if it's on the verge of total collapse just by looking at the silhouette of the buildings.
That is a phenomenal analogy.
Yeah.
And it gets right to the heart of the paper's argument, really.
Really?
Yeah. A single visual height field, your skyline, basically cannot distinguish between a loosely poured cone of sand, a heavily compacted cone, or a mound that looks totally fine but has a buried slip plane just waiting to avalanche.
Wow.
Classical descriptions usually define pressure as just, stuff pushing on stuff, weight pushing down.
Which isn't true.
Not in this Gibsonian framework,
Right,
no.
yeah.
Here, pressure isn't just weight. It is an aggregate gradient of these multiple channels interacting.
Oh, I see. A spot in the pile might look completely flat and stable to your eye, but internally, it could be deeply frustrated in its packing density or carrying an enormous amount of invisible shear debt.
Okay, so if you are listening to this, imagine the clutter on your desk right now, or maybe just a stack of books.
Yeah, perfect.
You have these 6 hidden channels dictating everything beneath the surface. And once you accept that, the paper makes a pivot that honestly blew my mind.
Oh, the unified taxonomy.
Yes. Because of these channels, the author proposes this unified taxonomy of objects. Entirely different objects are actually the exact same system.
This is where we start repairing that fragmentation of classical physics we talked about.
Right.
Under this theory, a stack of cardboard boxes in a warehouse is not a fundamentally different kind of thing than a messy pile of sand on the street.
Which sounds completely absurd until you think about the channels.
Exactly.
It reminds me of the states of water. Ice, liquid water, and steam look completely different to the human eye, right?
Yeah, totally different behaviors. They interact with the physical world in totally different ways. But if you zoom all the way in, they are fundamentally the exact same H2O molecules, just bound by different local rules of energy and movement.
That's a perfect parallel. A stack of boxes is really just a symmetry-restricted pile.
Symmetry restricted.
Yeah, it's a pile where the lateral toppling, the ability to fall sideways, has been mathematically suppressed by a very rigid lock state.
Right. And what about something dynamic, like a jam? Say, coffee beans stuck in a funnel, or even a literal traffic jam on the highway.
A jam is completely redefined here, too. We usually just think of a jam as stopped material.
The stuff that isn't moving.
Right. But in this Gibsonian framework, A jam is the local collapse of admissible passage under continued load.
A local collapse of admissible passage, meaning the pieces still want to move, the pressure is totally still there, but the geometry of the space suddenly makes it illegal for them to do so.
Yes, the material is still carrying a massive failure debt, but the system simply cannot find a legal local path to relieve it. It's a structural deadlock. And then there is the bridge.
Oh, the bridge is fascinating.
The author explicitly writes that a bridge is not a shape over a hole, which is just a profound shift in thinking.
It really is.
A bridge is a lock-dominated regime.
I was trying to visualize a lock-dominated regime, and the best thing I could come up with is a game of Jenga.
Ooh, I like that.
Yeah. Imagine you're playing Jenga and you pull out all the blocks from the bottom center.
Okay.
There is a hole there. There's no downward support at all, but the blocks above it don't fall because the friction and the pressure pushing them together side to side, that lock state, is so strong it completely overrides gravity.
That is exactly what a token closure regime is. The downward support is gone, but the lateral lock state is strong enough to maintain the bridge.
That's incredible.
It completely changes how you look at physical reality. But what's fascinating here is that to make this math work, the author introduces something that feels almost, I don't know, biological.
You're talking about the memory aspect.
Yes. The paper includes a concept called oscillatory corrections.
Okay.
In the calculus, there is a bounded oscillatory correction term. In a lot of classical math, that might just be a periodic garnish to make a wave function smooth out nicely, you know?
Just to make the math look pretty.
Exactly. But here, the math literally contains a formal channel for history dependence.
The object physically remembers its own past.
It does. It has structured packing memory.
Wow.
It remembers if you poured the sand out of a bucket really quickly, leaving microscopic air pockets.
Wow.
It remembers if it was vibrated into place, settling all those pockets. It remembers if it was carefully stacked by hand.
That is wild.
The directional deposition history isn't just an abstract idea. It is a physical force, mathematically encoded right into the hidden channels of the object.
So if the pile physically remembers all this and is governed by all these hidden tensions we just talked about, how does that change the actual shape of what we are looking at?
Right.
Because clearly the single outline of the pile we see with our eyes isn't giving us the whole truth here.
Oh, it's giving us almost no truth. And that brings us to the biggest conceptual advance of the entire paper, honestly.
Which is?
Because of all these hidden dynamics, every single accumulation object does not have one surface. It has three topologically distinct surfaces.
Three completely different surfaces existing in the same pile.
Yeah, we have to stop seeing a pile as a single skin. The first surface is the occupancy surface.
Okay.
That is the visible outer skin. It's just the boundary of where the material happens to be sitting right now.
Okay, the skin, that one's the easiest to grasp.
The second is the lock surface. This is the top of the jammed or supported interior skeleton.
Okay, so keeping with a body analogy, if the occupancy surface is the skin, the lock surface is the skeletal structure deep inside that is actually bearing the weight.
Perfect. And then you have the third surface, which is the failure surface.
The failure surface.
This is the upper envelope of latent, hidden failure. It maps the exact boundaries where the object is right on the verge of catastrophic redistribution.
So to finish the body analogy, the failure surface is like an invisible stress map of muscles.
Oh, exactly.
Like imagine a muscle in your leg that is right on the verge of a terrible cramp.
Yeah.
You can't see the cramp on your skin. You wouldn't see it in an x-ray of your bones. But that tension is peaking, mapping a totally different invisible shape inside your leg.
That captures it perfectly. And the crucial physical mechanism here is that these three surfaces do not have to match up.
Wait, really?
Yeah, they diverge.
How so?
Well, think about a really neat, orderly stack of bricks. The skin and the skeleton, the occupancy surface and the lock surface, are basically in the exact same place.
It gets perfectly stacked.
Right. The outside is fairly supported by the inside. But if you have a loose, messy pile of gravel, the visible skin might sit way higher than the locked skeleton.
Oh, I see. You have loose gravel just resting on top, not structurally locked in at all.
Exactly.
And what about the failure surface, the muscle cramp?
That failure surface might be meandering underneath the skin like a buried fault line, totally invisible to the naked eye.
That is terrifying.
Or think back to the jammed funnel. The lock surface is acting like that Jenga bridge, holding everything up over the hole.
Right.
But the failure surface is probably spiking sharply right around the edges of the orifice where all the stress is concentrated.
So the visible skin on top of the funnel looks perfectly flat, but the internal geometry of support and danger is wildly chaotic.
Absolutely chaotic.
Now, it is one thing to theorize about hidden skeletal structures and buried fault lines, right?
Sure.
But the author of this paper doesn't just leave it as theory. They actually provide a mathematical proof, a worked toy system to prove exactly how our human eyes deceive us. Here's where it gets really interesting.
Well, the 2D worked example is brilliant because it forces you to stop visualizing and start calculating.
Let's walk through it.
Okay, the author asks us to imagine a two-dimensional slice of a pile. It is 5 columns wide.
Got it.
The height of the material in these columns goes like this: 1 unit high on the far left, then 2 units high, then 3 units high in the center, then back down to 2, and 1 on the far right. So 1, 2, 3, 2, 1.
So it looks like a cute pixelated little mountain.
Right, a perfect step pyramid shape. Now the paper gives us 2 different piles, pile A and pile B.
Okay.
To your eyes, they both have that exact same 1, 2, 3, 2, 1 visible profile. Their occupancy surfaces are identical.
But they have different histories.
Yes, pile A was loosely poured, pile B was vibrated and compacted.
Visually identical, but underneath, completely different worlds.
Completely different. Because it was loosely poured, pile A has an incredibly high shear debt sitting right at its shoulders, those columns that are 2 units high.
The sides of the pyramid?
Yeah. Mechanics of the pour left it with weak flank lunking, meaning the sides aren't supporting themselves well. Pile A has essentially created a buried failure structure.
So how does the math actually expose that?
We can see it explicitly in the paper's yield signal math.
Yeah.
The author calculates the failure threshold for these specific sites.
Okay.
In pile A, at those shoulder columns, the yield signals are positive numbers, specifically 0.08 and 0.115.
Wait, pause. 0.08, 0.115.
Yeah.
For someone listening who doesn't read W-field calculus every day, what do those decimal points actually represent in the physical pile of sand?
Fair question. In this specific calculus, 0 is the absolute threshold of stability.
Okay.
Anytime that yield signal number creeps above 0 into the positive copy, the site is considered failure active.
Uh-oh.
It means the mathematical debt has exceeded the structural income. The sand is ready to collapse.
Oh, wow.
So when you hear a positive 0.08, think of it as a flashing red light buried inside the pile.
But then you look at pile B, the one that was vibrated and compacted, it still looks like that same 1, 2, 3, 2, 1 mountain.
Exactly the same.
But because of its history, because the vibrations settled all those micro pockets, it has a highly cohesive lock architecture.
Exactly. And when we look at the yield signals for pile B, at those exact same shoulder spots, the numbers are negative 0.825 and negative 0.755.
They aren't just a little below 0, they are deeply in the negative.
They are heavily anchored. If pile A is a flashing red light, pile B is solid bedrock.
Wow.
In fact, in the entire compacted pile B, there's not a single failure active site. The identical rendered skin is concealing an entirely distinct latent failure structure.
If you're listening to this, really think about what that implies. This raises a massive critical question.
It does.
If human eyes absolutely cannot tell the difference between the dangerous, flashing red loose pile and the incredibly safe, solid bedrock compacted pile, how do we ever know what we are looking at in the real world?
It's the ultimate problem. If you cannot trust your eyes, you have to use a different sense entirely. You have to touch it.
Tactogrammetry, which sounds like a medical procedure, honestly.
It operates very much like one. Tactogrammetry is the inverse problem of this entire theory. Well, the forward problem is, how do these internal channels build the object? The inverse problem is, how do we read those internal channels from the outside?
Right, without destroying it.
Exactly. The paper suggests using a robotic probe equipped with a distributed pin array. This robot physically interacts with the object. It pokes it.
It's feeling out the internal channels.
Yes. The probe measures contact force.
Yeah.
It measures local displacement, which is basically how much the material gives way.
Okay.
It measures stiffness. It measures hysteresis, which is the time-dependent delayed response of the material bouncing back.
Like how fast it springs back into place.
Right. And it measures microscopic slip. By feeding these incredibly subtle physical outputs back to the W-field calculus, the system can digitally map the hidden packing density, the lock state, and the shear debt.
It really is just like a doctor.
It really is.
Imagine a doctor palpating a patient's abdomen. They are pressing down with their hands, feeling for stiffness, feeling for a swollen liver or a hidden internal inflammation long before any visible symptoms like a rash or a bruise ever show up on the surface of the skin.
That is the exact mechanical principle. And if we connect this to the bigger picture, this kind of tactile probing completely revolutionizes the concept of the digital twin.
Right, a digital twin. For anyone unfamiliar, that's when engineers build a highly detailed virtual simulation of a physical object, like a bridge or a jet engine, so they can test how it behaves without breaking the real thing.
Correct. But historically, a classical digital twin of a granular system, like a massive gravel bed or an industrial grain silo, is just geometry.
Just the shape,
It's just a fancy 3D scan of the outer skin. It assumes the inside is uniform.
which we now know is a lie.
Right. But a Gibsonian digital twin, it maps everything. It includes the hidden jam architecture. It includes the latent failure surface. It includes the directional memory of how the silo was loaded.
Which gives it actual real-world predictive power.
Massive predictive power. Because the physics dictate that the hidden failure surface rises before the visible occupancy surface changes.
Oh.
So a tactogrammetry probing system could detect an impending collapse through microscopic stiffness changes long before a single piece of gravel visibly slips.
It feels the invisible muscle cramp before the leg actually spasms.
It sees the future of the object by reading its present hidden tensions.
That's amazing.
For robotics, for structural safety, for industrial hoppers, for anything involving complex physical mechanics, this represents a profound leap forward. We no longer have to wait for the avalanche to start to know the mountain is unstable.
So what does this all mean when we zoom all the way out from the math, the W-field calculus, and the robotic probes?
Yeah, what's the big picture?
The takeaway here is that accumulation is not random clutter. What looks like a mess to our eyes is actually rendered order operating under incredibly strict local counting constraints.
Exactly.
A pile isn't just a heap of stuff. It is an active, internal, political arrangement negotiating tension, history, and gravity every single second.
I think the author perfectly encapsulates the entire philosophy of this framework
Right.
when they say that a collapse is not chaos descending from nowhere.
Right.
We like to think of avalanches or structural failures as sudden random acts of nature, but they aren't.
Not at all.
A collapse is simply the exact, mathematically predictable moment that the hidden failure surface finally reaches the visible skin. Understanding that and mapping those hidden states is absolutely crucial for our grasp of physical reality.
It really is. Once you grasp it, it permanently changes how you see the world around you.
Oh, completely.
So to bring it all back, I want you to remember that simple pile of sand or that stack of boxes we pictured at the very beginning of this deep dive.
The everyday stuff.
Exactly. If a mundane pile of dirt on the sidewalk is secretly this highly structured, discrete polity governed by a history-dependent network of hidden tensions, locks, and invisible surfaces, what other simple or messy systems in your daily life are secretly operating under rigid, invisible mathematical architectures?
That's the real question.
From the chaotic traffic jams you sit in on your commute to the random clutter sitting on your desk right now, what hidden surfaces in your own world are just waiting to be mapped?